Now the first step is we have to calculate the mean. So calculate the mean of the vector from each is equal to 2 minus, you have to fix the mean by pressing F and F4. So 2 minus 4.5, 3 minus 4.5, 4 minus 4.5, 5 minus 4.5, 6 and 4.5 and 7. All right, can we move forward? Now we will calculate the covariance of the data table. So if you go to data tab, data analysis, input range, output range. Oh, I made a mistake. 1 second. You have to select data in rows. So let us round off the covariance matrix. So the covariance matrix is 2.92 round off, 3.67 round off, 5.67 round off, and this will be the same 3.67, the diagonal value. So this is the covariance matrix which is rounded off, multiplied by the identity matrix. Lambda is an eigen for a matrix characteristic equation. The characteristic equation is determinant of m minus lambda into I is equal to 0. I is identity. So if you multiply 2.92 into lambda, 5.67 into lambda minus 3.67 into 3.67 is equal to 0. If you simplify this, lambda square 8.59 plus 3.09 is equal to 0. Then when you solve the quadratic equation, lambda is equal to 8.22, 0.38. These are the eigenvalues. So we have to calculate eigenvector is equal to lambda x. M is the covariance matrix. X is the eigenvalue. X is the eigenvector. And lambda is multiplied by x1, x2 equals to 8.22. We'll take the lambda as 8.22. So when we do the multiplication, 2.92 x1 plus 3.67 is equal to 8.22 x1, 3.67 x1, 67 x2 is equal to 8.22 x2. On further solving, 5.3 x1 is equal to 3.67 x2. 3.67 x1 is equal to 2.55 x2. So x1 is equal to 0.69 x2. So eigenvector is 2.55, 3.67, and PCA component 1, 2.55, component 2, 3.67. So ultimately it reduced the 6 variables to 2 components, 2.55 and 3.61. So this is the whole algorithm in a nutshell. The covariance matrix is calculated. From covariance matrix, we calculate eigenvalues. Then we take the highest eigenvalue and then we use the, we calculate the eigenvectors. From eigenvectors, we calculate the principal components. So this is the process of PCA, principal component analysis, through which we do data transformation from independent variables to principal components. So this is the calculation which we have done using the Excel sheet. What it is showing?
Like activity train.info, it's showing like none.
Because this is very large, na? 563 variables are there, na? The output is very large.
Okay, sir. Yes.
So it is not able to fit the data in the window. So what we have to do is let dot max underscore. Okay, because there are too many variables, na? It is not able to display this one.
Okay, sir.
But there are no missing values. You want to check, you can check. So y is equal to activity train dot activity, x is equal to activity train dot drop, comma, subject is like id, comma, axis is equal to 1. X dot shape, high dimensional data, 561 variables and 7,352 rows only.
Sir, why did you drop the subject, sir?
Subject is nothing but ID. All right, can we move forward?
Did they define, sir, that subject is like ID? Because the data in the subject is not in any type of series. It's like.
That's what, na, ID. It is ID only, na. In what you call biological studies, we don't use the word ID, we use the word subject. From sklearn dot decomposition, PCA is equal to PCA n underscore components. So how many components we want? I'm randomly choosing initially 280 as x by 2. A random value I've given. So x underscore PCA is equal to dot fit of x. The exact need to find the component or minimum in variance. So x underscore PCA underscore variance is equal to x underscore PCA dot explained variance x underscore PCA underscore variance is equal to NP dot cumulative sum NP dot round x underscore PCA underscore variance PLT dot plot. Now you can see from the graph there is a point at which this is becoming a straight line, right? Or if you can't find it from the plot, you can print the output. Now you can see here it is stagnating from 99.75. It is stagnating from 99.75. But if you see, there is very marginal difference after certain point. 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 into 9, 162. That is still large because for 7352, we can take 148 variables. So we will take 140 components. So we'll take components as 140. So 140 components, 7,352 variables, 140 components.
So once again, can you explain how did you calculate 140?
50 observations per variable. 140 into 50 is 7,000. We have only 7,000 rows. So from sklearn dot preprocessing, import label encoder, y is equal to label encoder dot fit underscore transform, PCA underscore final comma y, logic model, PCA final comma y, 98.96, logic model dot predict, PCA underscore final, classification report. This is the confusion matrix. Once you're done, please confirm.
Sir, then why have chosen the like 280, sir, in the first time n component?
Some random value you have to give.
But why, sir? Because you have chosen the n components is 140 by multiplying into 50 now.
Yes.
Because it's like an assumption to multiply with 50.
Yes.
Then what's the need of taking 280 at the first time, sir?
To check the model, whether the variance is stagnating or not. To check at which point the variance is stagnating.
But we have like just for knowing us, sir, then
We need to know the point
just
at
for us to know, sir, like
stagnating or not. We need to know whether the variance is stagnating or not. If I give 140, variance will not stagnate. You always need.
so then we have to give like above 140 value.
See, the first thing
Hello?
is we need to know where the variance is stagnating. We need to know the point at which the variance is stagnating. And we found out it is stagnating at around 195 variable or 195 components or something like that. Generally, if we have
Yes,
enough data, we will take 195 as our point. But we have lesser data, so we are going below 195. We are going to the point at which the change is minimizing. Like I told you, 2 points you need to check. The final number of components is defined by variance stagnating point or minimum difference in variance. Now, in our case, the variance is stagnating at 195 variables. As per rule, we have to take 195 variables, 195 components, but we don't have the rows. So the next option is we have to go.
That's why, no, sir, we are using PCA.
There. The
No,
first
sir.
rule is variance stagnation is the first rule.
We are in the loss of rows now. That's why only we are using.
The first rule is
Sorry, your voice is not getting.
stagnating is the first rule. If the first rule is not met, go to the second rule. As per this model, number of components is 195, but we don't have enough data. So I'm going to the rule 2, which is the minimum difference in variance. The first rule and the important thing is we always take where the point it is stagnating as the component value. If you don't have rows, we have to go to this rule number 2, where there is a minimum difference. In this case, the minimum difference happens to be at around 140.
And what is that? So XPCA comma variance comma 4 into 100. The comma 4 into 100. Why
we are rounding the variance. You know, variance is always a larger number, right? Variance is always a large number. Variance is always a very large number. Decimals, and you will get a lot of bigger values. To round it off to a smaller value, we have to multiply it with 100 and make it 4 decimal.
So for all the kind of data that when we are using PCA, we have to do this.
Very large number. Any data variance calculation will always be a large number. So we have to reduce the value to a smaller number for interpretation. So here we are reducing it to 2 decimal by multiplying with 100. First rounding off to 4 decimals, then multiplying with 100 will give you 2 decimals. See, we can take even lesser values also. See, this point, it is 0.05. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 into 9, 108 components or 107 components. You can see here, the variance is 0.05. So we can take 108 components also. So you have to find out at which point you want to take the minimum variance stagnation. All right, all of you are done. So this is the implementation on the test data. Just let me check the accuracy. 95% accuracy. So this is the implementation on the test data.
Sir, is scaling compulsory for dependent variables?
Dependent variable.
Is scaling is compulsory for dependent variable?
We don't do scaling on dependent variables. Scaling is done on what, guys? Scaling is implemented on what data?
Independent.
Only on independent variables. You should not scale dependent variable. If it is a classification dependent variable, we will.
Sorry, sir. Like encoding, sir. Label encoding.
Yes, encoding has to be done. If it is a numerical dependent variable, logarithmic transformation or exponential transformation will be implemented based on the skewness. So you have to do.
Yes, sir, encoding.
Encoder must be done on label dependent variable in classification data. Here classification dependent variable is text. So you have to convert it into numbers, right? So label encoder will do it. Yeah. Can I get some white? Steamed rice with the yogurt. Now, will the rice curd be enough for the rice? No. Will the curd be enough yogurt? Or do I need to add in? No. The curd will be enough, right? All right, guys. All of you got this. So on train data, we got 99. On test data, we got 95% accuracy. So from sklearn.tree, decision tree classifier. Tree is equal to decision tree classifier. Tree model is equal to tree.fit PCA underscore final, comma y. Tree model dot score PCA underscore final, comma y is equal to tree model dot predict PCA underscore final. Confusion matrix dot display from y, comma. So tree test is equal to tree model dot predict x underscore test underscore PCA. Dot from predictions y underscore test classification report y underscore test, comma tree test. So on test data we got 0.79. So slightly overfitting problem is there. So we have a overfitting problem. So we have to define the max depth. 81 and 98 overfitting is there. Max depth 8. So 93 and 82 slightly is there. So max depth 6. 88, 81 is okay. So classifier with depth of 6 or 7. Max depth 7 is better.